Hey students, in the last video we learned about the bandwidth signal to noise ratio trade-off. Okay, so here we are going to learn about the channel capacity when the bandwidth is infinite. Okay, that is what we are going to derive over here. So the reason why we are learning about this is because according to Shannon's Hartley theorem, the value of the channel capacity C is B log 1 plus S by N bits per second. Remember, the channel capacity can be represented in two ways, right? It can either be represented in bits per second, it can also be represented in bits per sample. If it is bits per sample, the equation will be channel capacity is the maximum value of mutual information. Alright, maximum value of I of x of y is the channel capacity. In bits per second, this will be the equation, that is B log of 1 plus S by N bits per second. So for a noiseless Gaussian channel, and a channel which has zero noise, in that case then the signal to noise ratio becomes infinite, right? This noise power becomes zero, so therefore signal to noise ratio becomes infinite. So therefore if signal to noise ratio is infinite, then it will become the channel capacity will also become infinite, right? So this is what happens when the signal to noise ratio is infinite. Okay, but what happens when the bandwidth is infinite? When the bandwidth is infinite, you have to remember that the channel capacity does not become infinite. Okay, the channel capacity can become infinite if the signal to noise ratio is infinite, but the channel capacity does not become infinite when the bandwidth is infinite, and that is what we are going to discuss in this video. Okay, so how we are going to derive this is that we use the basic equation, that is the channel capacity is equal to B log of 1 plus S by N. Okay, we all know what is N. N stands for the average noise power, which is given by N0 into B, right? Where N0 by 2 is the power spectral density and B is the bandwidth in hertz. So therefore I will substitute this N0B in this equation. So this channel capacity equation is now B log 1 plus S by N0B. Okay, now what I'm going to do is I'm going to multiply this equation with S by N0 and multiply this equation with N0 by S. Okay, again I'm going to multiply this equation with S by N0 and then I'm going to multiply this equation with N0 by S. So this I'll get this equation. Okay, so the reason why is because I want N0B by S over here, that is why. So I will get C is equal to S by N0 into N0B by S log of 1 plus S by N0B. Okay, now what I'm going to do is that I'm let X is equal to S by N0B. That is, in that case, if X is equal to S by N0B, then this term will become 1 by X and this will become X. So this will become S by N0 1 by X log of 1 plus X. Okay, that is channel capacity C is equal to S by N0 1 by X log of 1 plus X. Okay, so remember that the base is 2. Okay, remember for all the log functions what I'm writing here, the base is 2. That's why the unit is in bits per second. Alright, so if this is 1 by X log of 1 plus X, then this can also be written as log of 1 plus X raised to 1 by X. So therefore channel capacity C is equal to S by N0 log of 1 plus X raised to 1 by X. Okay, one of the advantage of this is that because we know that since X is equal to S by N0B, then when B tends to infinity, that is when the bandwidth is infinite, then X becomes 0. When the B becomes infinite, then the denominator becomes infinite and anything divided by infinity is actually 0. So therefore X becomes 0. Let C max be the channel capacity of the infinite bandwidth. Okay, so we are trying to find the value of this channel capacity, that is the channel capacity when the bandwidth is infinite, that is C max. So the equation for C max is equal to limit as B tends to infinite C, that is limit as bandwidth tends to infinite of this equation. Okay, so therefore, but we already know that saying B tends to infinity is also equivalent to saying that X tends to 0. So therefore limit X tends to 0 C. Now I'm going to substitute the value of this value of C over here, that is S by N0 log of 1 plus X raised to 1 by X. Okay, so in that case I can put this limit inside my log function. So this will become S by N0 log of limit as X tends to 0 1 plus X raised to 1 by X. Okay, so we already know that there is a limiting equation that is represented by this equation, which says that limit as X tends to 0 1 plus alpha X raised to 1 by X is actually equal to e raised to alpha, where alpha is the constant as being multiplied in the X. Okay, So this is one basic mathematical equation. So what I have, so here the value of, if you compare these two equations, you can say that the value of alpha over here is actually equal to 1. So therefore this is nothing but E. This whole thing inside the bracket is nothing but the exponential constant E. So therefore the channel capacity, now the channel capacity max, that is the channel capacity of infinite bandwidth, is given by S by n0 log e to the base 2. Okay, so log e to the base 2. So in that case, let's see what is the value of log e to the base 2. That is, if I take log basis 2 alpha e. So log e to the base 2 is actually equal to 1.44269541, or in other words, the channel capacity of infinite bandwidth is equal to 1.442695 S by n0 bits per second. This is the value of the channel capacity when the bandwidth becomes infinite. Okay. So hi students, in the last video we learned about the bandwidth signal to noise ratio trade-off. Okay, so here you are going to learn about two things, and one thing is the bandwidth efficiency and the other is the Shannon's limit. Okay, bandwidth efficiency is represented by the term called as C by B. That is, C by B is the channel capacity to bandwidth ratio. Okay, so this term is what you call as the bandwidth efficiency, right? And this Shannon's limit is actually represents the minimum energy to noise ratio required for an error-free transmission. That is where we apply the Shannon's limit. Okay, see, when we talk about energy to noise ratio, the reason why we are considering energy to noise ratio is because in our equation, that is, we know the equation for channel capacity, right? According to Shannon's Hartley theorem, the equation for channel capacity is given by C is equal to B log of 1 plus S by N. Okay, S by N, and we know this average, this N, right? N is the average noise power, right? So this N can be represented as N0B. So therefore this can also be written as B into log of 1 plus S by N0B. Remember, the unit of this channel capacity is bits per second. Okay, it's bits per second. That is in terms of information rate or transmission rate. Right? The unit of this channel capacity is the same as the information rate. Or you can also express, just to recollect all of you, we can also represent the channel capacity in terms of maximum value of mutual information. But there, the channel capacity unit becomes bits per sample. So if the unit of the channel capacity is bits per sample, then the equation is C is equal to maximum of IXY. That is the maximum mutual information. If the unit of the channel capacity is bits per second, then that represents the maximum information rate. Okay, and according to Shannon's Hartley theorem, the channel capacity is given by this equation, that is B log of 1 plus S by N0B, where N0 by 2 is the power spectral density of the noise signal and the B represents the bandwidth. Okay, and this S over here is what you call as the average signal power. So this S, this average signal power, you can express this signal power in terms of the equation S is equal to EB into R, where EB is the energy per bit, transmission energy per bit, and R represents the information rate or transmission rate. Okay, so just to remind all of you, the same R you have already studied using the equation that R is equal to sample rate into I of xy, right? This is another equation for the information rate of R. R is equal to sample rate into I of xy. So the thing about this equation is that, you see, in an ideal system, we know that the channel rate becomes maximum, R becomes maximum, and we all know that the maximum value of the information rate or the maximum value of the transmission rate is nothing other than the channel capacity itself. That is, C represents the amount of data that the channel could handle, right? The the highest amount of data that the channel could handle, and that is represented by the channel capacity C. So therefore, the transmission rate, the highest value of the transmission rate is equal to C. That is, the value of R should be, in an ideal system, the R should be equal to C. If R becomes greater than C, then the Shannon's negative statement comes into effect. That is, we all know, according to Shannon's negative statement, if R becomes greater than C, then you will never get an error-free transmission. That is, error will surely take place and there will be data loss, or there will be loss of information if R is greater than C. So therefore, the highest maximum value of R should always be equal to the channel capacity C. That is the very definition of channel capacity C. So in an ideal system, R is equal to C. Okay, so if R is equal to C, I can honestly say that S is equal to EB into C for an ideal system, right? For an ideal system, then the signal power becomes EB into C. Substitute this equation over here, I will get the channel capacity C is equal to B log of 1 plus EB into C by N0 into B. Okay, let me bring this B to the other side of this equation. So this will become C by B is equal to log of 1 plus EB by N0 into C by B. Like I already said, the C by B is called as the bandwidth efficiency. Or this can also be written as, you know, that this is log to the base 2, right? The base is 2. That's why we are using bits per second. The base is 2. So this can also be written as 2 raised to C by B is equal to 1 plus EB by N0 into C by B. Or in other words, EB by N0 is equal to 2 raised to C by B minus 1 by C by B, where C by B is called as the bandwidth efficiency. This is for an ideal system. That is, ideal system means when the channel rate is, or when the transmission rate is equivalent to the highest value, the maximum possible value, or the limited value, that is equal to this capital letter C. Now, what about in the case of a practical system? In a practical system, the channel rate is not equal to C, it is less than C, right? The R value, the value of R should be less than C. So, in a practical system, the transmission rate is less than the channel capacity. So in that case, then you cannot substitute the equation for the transmission signal power. You cannot substitute the equation for the average signal power as EB into C. It is always equal to EB into R itself. Okay, that is the problem. In a practical system, you cannot substitute the value of R is equal to C, because the value of R, that is the transmission rate, is always less than the amount that the channel could handle, that is less than the channel capacity. So in that case, then the equation that you are going to need to use is this equation. That is, since we cannot use the channel capacity equation, then the equation for R will now become R is equal to B log of 1 plus EB into R by H0 into B. Okay, or in other words, using the same process, using the same steps, I can now prove to you that, again, if I want, I can write like this. That is, R by B is equal to log of 1 plus EB by N0 into R by B. Okay, and this can also be written as EB by N0, just like in the previous case. This can also be written as 2 raised to R by B minus 1 by R by B. Okay, the reason why I am using this equation is also because the diagram, the graph between R by B versus EB by N0. The graph between R by B versus EB by N0 is what you call as the bandwidth efficiency diagram. Is the bandwidth efficiency diagram. Okay, so that is the graph that we are going to talk about over here. That is we know that we know if you compare this equation and if you compare this equation, the only difference over here is that here it is C by B, whereas here it is R by B. Okay, but if you look very carefully in both this equation, this value, since R is less than C, over here the transmission rate is actually equal to R, so there, and the value of R is less than C, so therefore this equation is always less than this equation, because here the channel rate is equal to its maximum value, which is the channel capacity itself. Therefore R is equal to C. Okay, so this equation is what you call as the capacity boundary. This equation is what you call as the capacity boundary, and we can now represent this equation using the graph, and this is the graph. This graph is what you call as the bandwidth efficiency graph. Okay, so here you can see this is the equation. This is what this blue line that you see here represents the capacity boundary, and that it happens only when R is equal to C. Okay, this is called as the capacity boundary. When R is equal to C. Okay, and the region for this, and the region for this, that is when the transmission rate is less than C, that is like I said, this equation is less than this equation, right? So therefore it represents the region below this line, below this boundary region. That is, this is the region that expresses the equation when EB by N0 is equal to 2 raised to R by B minus 1 by R by B. That is, expresses this entire region over here. That is the region for R less than C, where the error-free transmission is possible. Okay. Now, like I said, that when R is greater than C, then error will surely take place, right? That region is what you call as the this region is actually called as the forbidden region. That is the region where you are not supposed to give the value of R greater than C. You should not be greater than channel capacity, because according to Shannon's second theorem, or the Shannon's negative statement, it says that if the channel rate is greater than the channel capacity, then definitely error will take place. So therefore the error transmission will takes place when whenever the channel rate comes above this particular boundary. Okay, anywhere in this region. Okay, so this is a graph, and this graph we have the x-axis, and x-axis we have EB by N0, which is in decibels, and here in the y-axis we have R by B, and this R by B can either be expressed in decibels or it can be represented in terms of, in a logarithmic axis. Okay, any one of them you can choose. Okay, I'm choosing in decibels for now. So here in this graph, if you look very carefully, right, so here if I'm looking at this graph, I can now tell you what is Shannon's limit, right? You see, we already know that the channel capacity of infinite bandwidth is actually given by C max. Okay, C max is actually equal to 1.443 S by N0, right? We have already been learning about this equation, right? There is 1.443 S by N0, right? This is the equation when the channel, when the capacity is in infinite bandwidth. So infinite bandwidth means, you see, if you look over here in this graph, that is when B becomes infinite, right? When B becomes infinite, or when B becomes very, very large, then R by B ratio becomes very, very small. That is, it goes downwards. Okay. in this region. So what happens when the bandwidth becomes infinite? See, it also represents the minimum value of EB by N0, right? Because over here, when we know that Cmax is equal to 1.443 S by N0, right? So this can also be written as 1.443 into S can be represented as EB into Cmax, right? EB into Cmax, because here the transmission rate is now equal to the maximum channel capacity, which is the transmission rate is actually equal to the channel capacity of infinite bandwidth, which is Cmax. So therefore EB into Cmax by N0. Okay, now see what will happen. Now what is the value of EB by N0 over here? The Cmax will get cancelled, so I can say that EB by N0 is now equal to 1 by 1.443. Okay, and what is 1 by 1.443? That is 1 divided by 1.443 is actually equal to 0.693. So this is approximately equal to 0.693 EB by N0. This is the minimum value of energy per bit to noise spectral density ratio. This ratio is called as the energy per bit to noise spectral density ratio, and this value is equal to minimum value should be 0.693. okay, or it can, in terms of decimal, it is, let me see, it will be 10 log 0.693. and what is 10 log 0.693? let me see, 10 log 0.693 is actually equal to minus 1.5927, or it's approximately equal to minus 1.6 decibels. Okay, 1.6 decibels. That is, if you look over here, this is the value. See, as this line goes down, right, this particular value line. This value over here, minus 1.6 decibels. This is called as the Shannon's limit. Okay, where EB by N0, right, that is EB by N0 minimum. Okay, this is called as, it's equal to minus 1.6 decibels, and this is called as the Shannon's limit. Okay, the EB by N0 is called as the energy per bit to noise spectral density ratio. Okay, so this is called as the Shannon's limit. That is the minimum EB by N0 value. That is it is the value when the bandwidth becomes infinite. Why? Because bandwidth becomes infinite, because at that time this equation for R by B becomes very, very small. It comes to this graph. Okay. So one thing you need to understand about this bandwidth efficiency diagram is that it's divided into three regions. One region is when R is greater than C, which is not allowed, or when the error-free transmission is not possible. And the other region is when the R is less than C, and here the error-free transmission is possible. And the third is exactly when R is equal to C. That is when, for an ideal, for a perfect system, when the maximum transmission rate is equal to the channel capacity. Okay. See, the thing is about this is that, because the one thing we can learn about this diagram is that, see, for a system which is limited by bandwidth, okay, for a system that is having a less bandwidth, right, that is having a limited bandwidth, then the value of R by B becomes very high. It goes up. So in that, if it goes very high, then for those kinds of signals, it has already entered into the forbidden region, right? It has already entered into the forbidden region, right? Especially for operations that requires low bandwidth, right? That has already low bandwidth in that region. So since R by B becomes small, then R by B ratio becomes high, then it will enter this region. So in that case, we need a high EB by N0 ratio in order to bring this signal down to this region. We need to apply a higher EB by N0 region, EB by N0 value, in order to bring the signal to this region, okay? And if the signal has a high bandwidth, okay, like for example space communication and all that, if the region is having a high bandwidth, then only low EB by N0 is only required to bring the signal to this region. Okay, and as the channel capacity is if the bandwidth becomes infinite, then the minimum for a very large bandwidth is when the bandwidth becomes infinite, then the minimum EB by N0 ratio must be equal to 0.693 or minus 1.6 decibels. Okay, and this minimum value is what you call as the Shannon's limit. That is, no matter whichever application we are using, for a Gaussian channel, the ratio of EB by N0, the ratio of EB by N0 must be equal to 1 minus 1.6, or the minimum value must be equal to minus 1.6 decibels. Okay.